How are we doing? Welcome to today's episode of Mr. Castro's Chemistry Classroom. I'm sorry that I couldn't be in class today, but as we know, life must go on. What we're actually going to be starting now is a new unit, which I'm really excited about, and the unit is called Kinetics and Equilibrium. Okay. This chapter deals more with the rate at which reactions occur and whether or not they will occur. What I have here is an Erlenmeyer flask that has a little bit of solution in it, and I'm waiting for a reaction to occur. So, you could say that in order for it to go faster, you can try shaking it, you can try to put it on a hot plate. But one of the questions that we'll deal with in this chapter is, why does that do anything? Why can't you put two things in a beaker and just wait for the reaction to occur? What we'll find in this chapter is that there are some reactions that need a little bit of a push before they can occur. And one of the examples that we could see is with baking. When you put all the ingredients together to make a brownie, you don't just have it sit there until it becomes a brownie. You need to put it in the oven, set it to a high temperature, and then wait for the reaction to occur with heat. So one of the questions that we'll deal with in this chapter is, what does that do, and how does that affect the rate of a reaction?
By the end of this video, students will be able to use entropy to explain disorder in a system, use the collision theory to explain how reactions occur, and identify factors that affect reaction rates. Keep in mind, all of the topics that we learn in this video will be quizzed on Wednesday.
Okay, let's get started. So this is page 1 of our notes. The first thing that we're going to do is talk a little bit about spontaneous reactions. A spontaneous reaction is a type of reaction that readily occurs, but only under a specific set of conditions. The first set is going to be under conditions of greater entropy. Okay. This is the same thing as more disorder. Greater entropy is going to be what we talk more about in this video. The second thing is going to be lower enthalpy. Okay, so the two things that we need for a reaction to readily occur, okay, is having greater entropy and lower enthalpy. Again, this is what we're going to be doing in a couple of days. This is what we're going to be focusing on today. In order to give us an introduction to entropy, let's watch this short clip.
Entropy. When I think of entropy, I think of my 4-year-old daughter. If she comes into a room, no matter how clean it is, pretty soon it's chaos and disorder, and we've got to go in there and kind of fix everything up and try to straighten it out. So basically, entropy is the amount of disorder within a system. So let's look at an example of entropy. Let's say I've got water, and I've got that water frozen in a nice little ice cube, okay? And this ice cube has a lot of order and a lot of structure. And all these molecules are held together in these very tight, precise bonds, okay? Now, if we let that ice cube melt, it's going to gain entropy. It's starting to gain energy, and it's starting to move around, and it's losing that order and that structure. It's moving towards disorder. And so now our ice cube, I'm going to put it into a little cup, is going to become water with more energy and more motion and more disorder. If we let that continue to evaporate, it's going to turn into water vapor, and it's going to become all the molecules in the air, in water vapor. And that's got a lot of energy and a lot of disorder. And those molecules are going everywhere and bouncing and colliding into other things. So that is a system with a lot of disorder, high entropy. But as the water is going from order to disorder, that energy is also causing an increase in entropy in the air molecules around it. As the ice is melting, the air around it is getting cooler, and that's causing a decrease in entropy. And as the water evaporates, that evaporative cooling is cooling off the air, which causes a decrease in entropy in the air. So entropy can go in two directions, and oftentimes it goes in two complementary directions as one thing heats up and another cools off.
So that video was good because it summarized entropy, and also it talked a little bit about how there's a balance between shifting to more entropy and shifting back to less entropy. Okay, Entropy itself is the measurement of disorder or randomness in a system. So entropy is a measurement that we can have that measures the disorder or randomness that there is in a system. Okay. We find that if we increase the disorder, we're going to be increasing entropy. Okay. So again, this is just explaining what that measurement is for. Just like for kinetic energy, we're saying that we're going to be increasing temperature. Okay, that's the same kind of relationship here. Here's a diagram that can be used to show entropy. So on the left, we have something that is highly ordered, right? Very organized, very low level of randomness. And in this case, that means that it has low entropy. As we increase entropy, now we start to have something that looks like the picture on the right. And we can see this in the way that the shapes on the right are more spread out and random in the way that they're positioned. Technically, in chemistry, we don't really mean that there's a disorder in the position, where all these are all disorganized. We really want this to show energy. In this case, the energy is very ordered, very organized, and in this case, the energy is displaced. Naturally, the system, or the universe, wants to become more random, more messy. We can see this in the way that things naturally disintegrate, things naturally break apart. It doesn't matter how nice you try to keep something, it will eventually break down. So the question here is why? Why does a system naturally want to become messy or more random? Well, the answer is that it takes energy to decrease disorder in a system. For example, there are far more ways to mess up a clean room than there are to make it clean again. And we can see that in this picture here with this little boy who has totally destroyed his room and says to his mother, "I blame entropy." It's because things naturally want to be messy. It takes energy to clean the room. Just like in our reactions, it takes energy for those particles to collide in the special way that allows them to form more highly organized arrangements. And for this reason, reactions are usually expected to proceed in ways that increase entropy. Okay, so now back up here, we took a look at this example with the room, and this relates to how molecules can collide. So obviously, like we just said, there are many more ways that a particle can produce disorder, and only a few ways that we can produce a new compound. So we can only have this occur in specific ways in order to form a highly organized arrangement. Reactions are usually seen to proceed in ways that increase entropy. Okay, let's turn the page over to page 2. In this example, we're going to look at a physical way that we can identify which of these will have more entropy. So let's start with our solid. So we can see here that my solid, I have my nice little block, and we already know about solids, right, in the way that they have a definite shape, a definite volume. Their particles are vibrating, but not really moving or changing position. Because of this, we can say that this has a great amount of order. Okay, so we're going to put great order, right? Solids are very organized in their arrangement. Because they have great order, this gives them less entropy, right? They have a low level of randomness. If we look at our liquid here, liquids have more energy, they're able to change their position. They have a specific volume, but no specific shape. They can move around. This leads us to believe that they have more randomness, and compared to solids, they have higher entropy. Their disorder is greater. And in our last example, we have a gas. A gas has the highest amount of randomness, and it gives us the highest entropy. So this has the maximum randomness, and we are left with the highest entropy. Now we'll go to our chemical example. Generally, if we're talking about chemical equations, we have our reactants on one side and our products on the other. And in order to figure out which side will have more or less entropy, you want to look at the one that has the greatest number of molecules as being the side with the more entropy. So if we take a look at this, we have a synthesis, almost like a synthesis model here. So if we're synthesizing something, we should recall that we are creating something. So I'm just going to put H plus, Cl minus. Okay. If we were to combine those, we could synthesize HCl. Okay. Because we're going from two compounds, right, two molecules, to one compound, we are becoming more ordered, and we're going to have less randomness or entropy. In the other hand, we have decomposition. So of course we're going from a compound and we're breaking it down to two different products. So let's put our example here. Let's say that we have hydrogen sulfate. Okay, this is a big compound, and we're going to decompose it into water and SO2. In this case, we have one compound that becomes two. So because we have more pieces here, we have more molecules, we're going to have less order and more entropy. So we can just take a look at the questions like this and just kind of compare them and see which would have more or less entropy based on the number of molecules. Next, let's go to kinetics. So kinetics is a branch of chemistry that is concerned with the rates of chemical reactions. What I mean by rates is how fast and how many moles are produced. Okay. Also, kinetics deals with explaining the mechanism or steps of a reaction. Okay. So kinetics deals with these two things here, which is going to be the focus of this unit. The way that we explain kinetics is through the collision theory. Okay. So the collision theory is used to explain the factors that affect the rate of reaction. This goes a little bit more into the introduction that I had in the very beginning of this video. For a reaction to occur, the reactant particles must have enough energy and collide at the correct angles for a reaction to occur. So in general, they need to collide with enough energy and at the right angle or orientation in order for a reaction to occur. This is very important for chemical reactions, and this is called an effective collision. Here it is spelled out, effective collision. Here's what I mean by effective collision. In this case, we have an ineffective collision up at the top here. What I mean by ineffective is that our products were not different than our reactants. So what we ended up having was NO plus O3. They hit each other, but not at the right orientation, and our products didn't change. In an effective collision, we have NO and NO3. They hit each other at just the right angle to yield new products, NO2 plus O2. So in this case, because they hit each other at the right angle, and probably with enough force, they were able to form a new product. In this case, we can sort of think about chemical reactions being sort of miracles, that they hit each other at just the right angle. But keep in mind, this is happening at the molecular level and the atomic level. So this is happening in instances. Here's an example of what this might look like in solution. So we have all these little particles moving around, and you'll see that most of them have a lot of energy. And the ones that do have enough energy and hit at the right position or orientation will have enough to form a molecule. The ones that are moving a bit slower, those are probably not going to have enough energy, and they're probably not going to hit the right angle in order to form a new compound. So, next we will turn to page 3, where we will go into the factors that affect the rate of reaction. The first one that we have here is the nature of the reactants. Basically, we're saying that it does matter what kind of reactants we're working with. Okay, so for this we need to recall that chemical reactions involve the breaking of existing bonds and the formation of new ones. Okay, the key thing here is that reactions are going to go faster
when there are less bonds to break or form. So in a situation where we don't have as many bonds, those are the ones that will go faster. Okay. The reason for this is because as we break or form bonds, this requires an effective collision. And if we come back to kind of what we just talked about, effective collisions only occur if we have enough energy and if it's in the right angle. Okay, so this is going to take time and energy, so obviously if we can avoid this, that would make the reaction go by faster. So let's take a look at this example below. In this equation, we have ourselves this coordinate covalent bond is going to form, and we have to break this bond and then form a new bond. So this, obviously, like I said, takes time and energy, and that's going to slow things down. If we don't have to do this, then the reaction would go quicker. So what we generally find is that covalently bonded substances are slower to react because there are more bonds that must be broken or formed. So if we have a covalent bond, this is the instance where it would probably occur slower. On the other hand, if we have an ionic bond, these are going to occur fast because they can collide at any angle. They are ions. So as long as the charges interact, then there's not necessarily going to be a bond to slow us down. So the ionic bonds are going to dissolve faster than covalent bonds. Hopefully this is pretty straightforward, but just in case, I want to show it with these molecular models. Again, these make great gifts for any chemistry nerd. What we have on this side are two covalent compounds. What I have here, this we can see is a covalent compound because these little pegs stand for bonds. Okay. And then what we have on this side, these are cations and anions, okay? And you see that by the different colors. If we're forming bonds, what we see is that it takes time to physically create the bonds here. Okay, so you see that took about a second. What we also have to keep in mind is an effective collision. If these hit at a wrong angle, we're not going to get any interaction. This has to be just the right orientation for my pegs to go in or for my bonds to form. On the other hand, if I have ionic compounds, these are not true bonds. These are just attractions. So I could just move these near each other, and they are attracted to each other enough to just be bonded together now. On the other hand, if we're breaking bonds, again, if we have a covalent compound, I have to physically go in there and break the bond. That takes energy. Whereas in our ionic compounds, these are just attractions. We can break them apart because there's no true bond holding them together. And now down at the bottom we have concentration. So if we have something that's more concentrated, what that means for the sample is that there will be more frequent collisions. If we have an increase in the number of collisions, this is going to increase the likelihood, right, the chances that some of those collisions are going to be effective collisions. Once we have more effective collisions, that's when we have a reaction occur. This can be shown in the picture below. On the left here we have a low concentration. We're going to have fewer collisions because, of course, there are less to collide with. On this side we have a high concentration, and because we have more, if we have the same volume here, I'm assuming, the concentration will be higher, there will be the same amount of space as this one, and because of that, we will have more frequency of collisions. Okay, we are really going through this. Turn over to page 4. This is where we will find pressure. Now, pressure is a trait that affects the rate of reaction only for gases. Okay, so we see that if we change the pressure, that's not going to affect liquids or solids. If we change the pressure, this is going to cause an increase in the concentration for gases. And I have a picture to the right that will explain that in a moment. When I increase the pressure, we are going to have an increase in the concentration. What this does for us is that for the gas, we have an increase in concentration. And just like we said before, if we have more concentration, we have more frequent collisions. Okay, this gives us the more likelihood of having effective collisions, okay, and just like we said before, this increases the reaction rate. Let's take a look at this on the image to the right. So if we take a look at this first piston here, we have a pretty reasonable volume, and all these gas molecules are colliding.
if we look at the piston here on the right, we see that we have now increased the pressure, which is pushing this down, and we know that gases don't have a definite volume or shape, so if we change the pressure, we're also changing the volume, because now the gas molecules are just going to condense so that they could fit into that new volume. Because we have a smaller volume, the concentration is comparatively higher here, and that's why we're going to have more collisions. Okay, next we have temperature. Now, you might see this in the lab. When you increase temperature, what this ends up doing, as we've already said before numerous times in the class, is that it increases that kinetic energy. If we increase the kinetic energy, that means that particles move faster. Okay, so if we're increasing the kinetic energy, this causes particles to increase in their speed. When we increase in their speed, as you can see in these two diagrams, we're going to increase the number of collisions, right? We're going to increase the frequency because they're moving faster. And again, just like we said before, the whole aim of these has been to increase the likelihood of an effective collision. Okay, next we have surface area. Surface area is the measurement of the area around the object, not including the inside volume. Okay, so what we find is that the larger the surface area, the more exposed particles that can react. Okay, this is a good thing. So we need to increase the surface area to speed up our reaction. What this does for us is it leads to more collisions. And just like we've seen before, it increases the rate of reaction. Okay, so in general, increasing the surface area increases the rate of reaction. Okay. Think back to how we were dissolving ionic compounds. As we added ionic compounds, you'll see that they dissolve much quicker, and that's because of their surface area. Okay. For example, if you have powdered magnesium in HCl, it's going to react faster than a solid piece of magnesium because powdered Mg has more surface area. Now what I would like to do is just explain that picture that I have on the right that has all those little dots. Okay, so first I'm going to draw a block of ice. You don't have to draw this, I'm just kind of giving you a picture. So the reason I'm drawing this is because in the olden days, before they had ice boxes, right, refrigerators, they used to transport their ice in order to refrigerate all of their products. What they would end up doing is getting a piece of glacier and just cut out a gigantic chunk of ice. And this would preserve itself while they ship it over. The reason why this works better than if you had little tiny ice cubes is because of surface area. Now, we've already said that if you increase the surface area, we are going to increase the rate of a reaction. So it makes sense that if we do the opposite and decrease the surface area, we're going to decrease the rate of reaction. What this does here is if we have a block of ice, and let's just say this is a 4 meter by 4 meter box, that means that if we were going to have heat applied to this, just like you would if we were carrying a block of ice in a freight train, the heat is going to be acting on all the sides of this box. On the inside, however, which is not in contact with the outside, it can stay relatively cold. So this is why this is better than having something where it's broken up into little pieces, because in this example, we have less surface area. Okay, so let me explain with these dots. So let's just say I have an ionic compound, and voila, here is my cube that's 4 by 4. So if I was going to apply something here, if I was going to have my reaction, let's just say I was adding water. I'm trying to dissolve this cube of salt in water. Okay. If I add water, just like I'm adding heat to all the sides of this ice box, if I add water, it's going to interact with just the sides of this cube. Okay, so the area would just be the outside, the inside would not be touched, and water would have to get through this first line of defense before it gets to the inside. This is totally different than if I had something like this, where we only have 4 boxes. And I'll do another one with 4 boxes. Because now if I was going to add water, now it's going to add itself to a smaller box, and if I continue to do that, this is actually going to go by quicker than trying to attack all sides until we get to the very center here. this is going to continue on and on until even if we got to little tiny dots, the surface area on these will be, of course, more. But we're going to have more of those. So if I was going to add water, this is going to react more quickly because now I can attack all the sides of the boxes here, the surface area. So this is much quicker than having a gigantic cube. That's why when you drop a cube of salt into water, you got to shake it a little bit. You want to break these little pieces so that the surface area is larger here. Okay, so now that I've explained my little dots over here, I want to show you what this would look like in the lab.
Let's look at the rate of the reaction of a very large surface area. Now with a small surface area, you can see we don't get that fast reaction.
Now we go to our final category here, and this is our catalyst. Okay? A catalyst has the main job of lowering the amount of energy needed to start a reaction. This is also called activation energy. Okay? So by lowering the energy needed, it's going to give us a faster rate of reaction because the particles are going to need less energy in order to react and have those effective collisions. Here on the bottom we have our image of our catalyst, and some teachers use the term lock and key, and I do like how that summarizes basically what's going on here. However, technically, chemically, that's not what's going on. So you can definitely use the term lock and key in any class, but of course I just want to go over what's really happening. Lock and key model basically says that you have your catalyst here, and your reactants are going to bond at these areas here, as you can see, and now that almost like how they fit into a lock, these will basically now combine, and we have our products. That's the gist of what's going on, yes, but technically what's happening in terms of the collision theory is that the catalyst here acts as almost like a hand that takes the two reactants and holds them in just the right orientation for a reaction to occur. This is great for a reaction because now the molecules don't have to knock around randomly. They interact with the catalyst, and now it doesn't take as much energy for them to hit each other at just that right orientation to form a product. In our last couple of minutes, I just want to go over all the stuff that we've done. You don't have to copy this down, but I just want to take a minute to show you what we've done. So in order for us to increase the rate of the reaction, we need to keep in mind the collision theory, which basically states that if we want to increase the rate of the reaction, we need to think about how the molecules are reacting in terms of their energy in their collisions and in the angles that they collide. The way that we can improve the likelihood of having a chemical reaction and having those effective collisions is by doing the following. Having compounds that have less bonds in them, having more concentration of our reactants, increasing the pressure if we're talking about a gas, adding heat, increasing the surface area either by breaking the compound down into pieces, and adding a catalyst. The way that this fits into entropy is that reactions usually try to become more disordered. In order for us to have a reaction occur where we are creating something, we need to increase the chances of that happening and decrease the energy. That's where a catalyst comes in, and that's where these things come in to make more of those effective collisions. I hope that this was helpful. If you have any questions, hold them off until tomorrow when I see you next, and I hope you have an excellent day today.